Welcome back, everyone, to the deep dive. Today we're tackling something, well, kind of counterintuitive, actually. We have these incredibly powerful AI systems, large reasoning models, right? They can write poetry, generate complex code, all sorts of amazing things. But give them a basic table, like a spreadsheet, things start to get surprisingly messy.
That's exactly it. It's a fascinating paradox. And what's maybe even more worrying is that the systems we built to check their reasoning, the process reward models or PRMs, they often fail right alongside them when tables are involved.
Right. So today we're really digging into why this happens with structured data, specifically tables. And we're going to unpack a really interesting solution called Tattoo. It's apparently much smaller, but somehow manages to fix this big problem.
Yeah, it's all about tabular reasoning.
Hmm.
And, this isn't some minor edge case. This capability is fundamental for so many applications. Think numerical analysis, financial stuff, even just basic fact-checking against data. If the AI can't reliably read a table, that's a huge issue.
Okay, so let's quickly define the key players here for everyone listening. First, you mentioned LRMs, large reasoning models. These are the main AI brains doing the thinking, right? Like the big models we hear about.
Exactly. Those are the engines generating the reasoning steps, the potential solutions. Think of models like DeepSeek or Qwen, those sorts of systems. Then you have the PRMs, the process reward models.
The critics?
Kinda, yeah.
Yeah.
Think of the LRM as, say, a student doing math homework, showing their work step by step. The PRM is like the teacher, looking at each step and giving feedback, a score, saying this step looks right, or this one seems off. It provides supervision during the reasoning process.
Okay, got it. LRM does the work, PRM grades the steps. So the mission for this deep dive, based on our sources, is figuring out why these PRMs, these AI teachers, seem to be, well, asleep at the wheel when tables come up. We're going to look at why they fail and how this new approach, Tattoo, which is tool-grounded, apparently gets amazing results with way fewer parameters, like
Yeah,
8 billion versus models 9 times bigger.
precisely. It suggests there's something fundamentally different and arguably better about Tattoo's approach compared to the standard PRMs.
Okay, let's unpack this.
So first, we really need to understand the problem itself, the performance bottleneck. Researchers found that even when using these sophisticated PRMs to guide the LRMs on table tasks, the performance just plateaued really quickly.
Plateaued. How so?
Well, they call it observation one in the research.
Hmm.
Basically, accuracy hits a ceiling. Let's say you generate more potential solutions, right? You ask the LRM for, say, different ways to solve the table problem and use the PRM to pick the best one, you get certain accuracy. Then you think, okay, let's generate more options, maybe N 32 solutions, give the PRM more to choose from.
You'd expect the accuracy to keep going up, right? More chances to find the right answer.
Exactly. That's what happens in lots of other AI tasks. But here, on table reasoning, the accuracy barely budged past N8. Going to N32 gave almost no extra benefit. The PRM just wasn't helping anymore beyond a small number of samples.
Huh. That is weird. It's like the teacher gets overwhelmed or just stops being useful after looking at a few attempts. So that points to a real flaw in the PRM itself, doesn't it? If it's good at grading text reasoning, why does it fall flat with tables?
That's the million-dollar question they dug into. They did an error analysis on hundreds of incorrect responses, trying to pinpoint why the PRM was letting these errors slip through, and they found two massive culprits. Together, these accounted for a staggering 82% of all the mistakes the PRM failed to catch.
82%. Okay, what are they?
The first one, the biggest chunk at nearly 48%, is what they call table retrieval failure.
Retrieval failure, meaning not finding the right table.
Or, more subtly, not verifying that the LRM extracted the correct part of the table. The LRM might say in its reasoning, okay, I need to look at rows 5 to 10 and column C, but the standard PRM just reads that step and says, sounds logical, without actually checking if rows 5 to 10 in column C are the relevant data needed for the question.
It doesn't check the facts, just the logic flow.
Precisely. They ran this really clever experiment to prove it. They took a very powerful baseline PRM, a 72 billion parameter model, mind you. They gave it two scenarios to grade. Scenario A, an LRM reasoning step using the genuinely correct subtable needed for the task. Scenario B, an LRM reasoning step that looked similar but used a completely random, irrelevant chunk of the table.
Okay, so one used real data, one used garbage data. What did the PRM say?
This is the shocking part. It gave almost identical reward scores to both steps. The distribution rewards was basically the same whether the LRM was using the right data or junk data.
Wow. So the takeaway there is the standard PRMs are just blind to whether the LRM is even looking at the right information.
Exactly. Takeaway 1. Insensitive to table retrieval correctness. They check the reasoning style, not the factual grounding in the table itself.
Okay, that's nearly half the problem right there.
That-
What's the second major failure? That was about 34%, you said.
Yes, 34.3%. This one's called schema interaction failure. This happens after the retrieval step when the LRM is trying to actually use the data it's supposedly retrieved, doing calculations, comparisons, aggregations, that kind of thing.
So it found the data, or thinks it did,
Yeah.
and now it's trying to do math on it.
Right. And this is where a fundamental limitation of these autoregressive models kicks in, something called locality bias.
Locality bias sounds technical. Can you break that down?
Think of it like AI short-term memory. These models generate text step by step, right? And each new step pays most attention to the immediately preceding steps. Now imagine the LRM retrieves the correct table chunk way back in step 3, then it does a bunch of other reasoning steps, step 4, 5, 6, maybe clarifying the plan, and then way down at step 20, it finally needs to do a calculation using the data from step 3.
Ah, I think I see. By step 20, the crucial table data from step 3 is far away in the sequence.
Exactly. Because of locality bias, the model at step 20 is mostly paying attention to steps 8, 10, and 19. It effectively, well, it sort of forgets or loses the precise context of the table data it retrieved so much earlier. It's not local anymore.
So it might perform a calculation that looks okay in isolation at step 20, but it's using corrupted or forgotten data from step 3.
Precisely. And the PRM, which is also often localized and just grading step 20 based on steps 18 and 19, also misses this long-range dependency failure. It checks the math formula maybe, but it doesn't easily verify if the inputs to that math are still consistent with the table retrieved way back when.
Okay, that makes sense. So takeaway 2 is standard PRMs fail to catch these errors because they can't effectively track these long-distance connections between when data is retrieved and when it's actually used.
You got it. Locality bias in the LRM and the PRM's inability to overcome that during verification.
So these two things, blindness to retrieval correctness and inability to track data used over long reasoning chains, explain why performance just hits a wall.
That's the core diagnosis, and it's this diagnosis that directly motivated the design of Tattoo. They knew they needed something different.
Right, so Tattoo table aware and tool integrated, how does it actually address these two huge failure points? What's the strategy?
The fundamental idea behind Tattoo is to provide much more robust and targeted supervision, specifically for these table-related operations, while still handling the regular text-based reasoning. It tackles the two failure modes directly.
Okay, how?
It has two key design innovations. First, table-aware reward decomposition. Instead of the old PRM just giving one single score for how good a reasoning step is, Tattoo breaks it down.
Breaks it down how?
It calculates two separate reward components for each step. One reward, let's call it Karena, grades the inner thinking, the pure text-based reasoning part. And a second separate reward specifically grades the parts involving the table, either the initial retrieval step or a later schema interaction step.
Ah, so it uses a different specialized lens to look at the table stuff versus the general logic stuff.
Exactly. It allows for targeted validation. If it's a table retrieval step, the board component is designed to be much more critical about correctness. If it's a calculation step, Sport focuses on that.
Okay, that deals with the targeting. But there's still that problem of how the PRM actually verifies something objective, like a calculation or a specific cell value. If the PRM is just another language model, can it make the same mistakes?
That's the million-dollar question, and it leads to the second and arguably most revolutionary part of Tattoo: tool integration in verification.
Tools, like external programs.
Precisely. Tattoo doesn't try to perform the table operations or calculations itself during verification. That's where the old models failed. Instead, it learns to delegate these objective checks to external, reliable tools.
Okay, like what kind of tool?
Two main types. First, computation tools. Think of it like giving the PRM access to a calculator or a mini Python interpreter. If the LRM makes a claim like the sum of column B is 542, Tattoo doesn't try to read the numbers and add them up in its head. It generates a tiny Python script like sum column B values and executes it. It compares the LRM's answer, 542, to the actual output of the reliable computation tool.
So it gets an objective ground truth from the tool.
Exactly. And the second type is table lookup tools. These are like utilities for interacting with data structures, maybe similar to Panda's data frame functions. If the LRM claims the value in row 7, column name is Alice, Tattoo can use a lookup tool to query the actual table data provided and verify that specific cell's content objectively.
Wow. Okay, so the PRM stops being a judge trying to redo the work and becomes more like a supervisor who knows how to use reliable instruments to check the work.
That's a great way to put it. It leverages external execution for reliable, precise supervision on those steps that demand factual or numerical accuracy.
But hang on. Training a model to do this sounds incredibly data intensive. You need tons of examples of reasoning steps correctly linked to the right tool calls and their outputs, right? How do they even create that data? Sounds like a nightmare.
It definitely required a clever approach. They built what they called a data curation pipeline. First, they generated a lot of reasoning trajectories, about 60,000, using very capable LRMs as a starting point, models like DeepSeek R1 and Claude Opus. So they had high-quality reasoning examples.
Okay, so they have the reasoning chains. How do they inject the tool use for the verification part?
This is the really neat part. Tool use synthesis. They didn't manually annotate everything. They developed methods to automatically identify steps in the LRM's reasoning that could be verified by a tool, like a calculation or a lookup. Then, within the verifier's rationale, the PRM's explanation of why it's giving a certain score, they automatically replace the PRM's own attempt at that calculation or lookup with a call to the appropriate tool and the tool's actual executed output.
Ah, so they synthesize the verifier's process to show reliance on the tool.
Exactly. It wasn't just about getting the LRM to use tools. It was about training the PRM to trust and leverage the tool outputs when assigning its reward scores and generating its own justification. It learned that the tool's answer is the ground truth for those steps.
That's really clever. Okay, so they have the data engine. Now, how do they actually train Tattoo using this tool-integrated beta? You mentioned a dual-stage process.
Right. Simply having the data isn't enough. You need to shape the model's behavior effectively. They use a two-stage training paradigm. Stage 1 is supervised fine-tuning, SFT. This is where the model first learns the basic patterns of tool-integrated verification from that curated data set.
So learning to recognize when a tool is needed, which tool to call, and how to incorporate its output into the score.
Exactly. And crucially, during SFT, they also specifically train the model to fix that locality bias problem we talked about earlier. It learns to automatically prepend the relevant table prefix or schema information to steps that are doing schema interaction, even if the retrieval happened much earlier.
Oh, interesting. So it forces the context back in, making the table data local again for the verification step.
Precisely. It directly counteracts the forgetting issue. So SFT teaches the patterns and fixes the locality problem. But then comes stage 2, reinforcement learning, RL optimization.
Okay, RL. This is where you really refine the policy, right? Make it more robust.
Yes, they use an RL framework, specifically a modified version of something called group policy optimization, GRPO, but the key is the reward signal they use during this RL stage. They engineer the reward signal for each step out $1 to really hammer home the importance of tool use.
How is the reward structured?
It has 3 main parts based on their equation 3. First, standard label matching, encouraging the PRM to predict the correct overall label. Is the LRM step correct or incorrect? Second, confidence calibration, basically stabilizing training by encouraging the PRM to be more confident when it's correct. But the third part is the crucial one, a tool grounding term. They use Lambda tool for it.
Tool grounding. So this specifically rewards the model for using tools correctly.
Yes. This component explicitly incentivizes the PRM's verification rationales to effectively incorporate and rely on the tool outputs. It positively reinforces the behavior of delegate and trust the tool that was learned during SFT. And they showed how critical this is when they did ablation studies turning off different parts of the system to see the impact removing this tool grounding reward term caused the biggest performance drop, like a 4% absolute drop on one of the key benchmarks.
Wow. So the RL phase is really about forcing the model to not just know about tools, but to actively prefer using them for verification when appropriate.
You've nailed it. And they have a fantastic case study, figure 9 in their paper, that shows the difference this RL stage makes. It looks at a step where the original LRM had to calculate a sum, say adding 10,000 and 12,460. The correct answer is 22,460.
Okay, what did the SFT stage PRM do before RL?
The SFT stage PRM, even though it had seen tool examples, still defaulted to its old ways. It tried to reason about the sum internally, maybe looking at the numbers in the text. And it made a mistake. It calculated something like 16,920. Because its internal calculation was wrong, it then incorrectly judged the LRM step, assuming the LRM got it right, as incorrect and gave it a negative reward, -1. The verifier itself failed.
The critic made the math error. Okay, so what happened after the RL stage with the tool grounding reward?
Completely different behavior. The RL-trained tattoo sees the sum as needed. It immediately thinks, calculation required, use the tool. It generates the Python code snippet 1000 plus 12460, executes it in the sandbox computation tool, and gets the output, 22,460. It compares this objective tool output to the LRM's answer. Assuming the LRM was correct, Tattoo now correctly judges the step as correct +1 because the reliable tool confirmed it.
That's a perfect illustration. The RL stage fundamentally shifted the PRM's behavior from trying to reason internally to reliably delegating.
Absolutely.
Yeah.
They found that after RL training, this kind of tool integration in the verifier's process increased by over 26%. It learned to rely on the tools much more consistently.
Okay, the mechanism makes sense now. The decomposition, the tool use, the dual stage training, it sounds very thorough. So the big question, what was the payoff? Did Tattoo actually deliver in terms of performance?
Oh, absolutely. The results are quite dramatic, actually. Remember, Tattoo is an 8 billion parameter model. When used to supervise and select answers from a policy LRM at inference time, it improved the LRM's final accuracy on complex tabular reasoning benchmarks by an average of 30.9% compared to using no PRM or simpler PRMs.
A 30% jump, that's huge. And how did it compare to those big baseline PRMs like the 72 billion parameter one?
It consistently beat them. Despite being almost 9 times smaller, Tattoo achieved superior verification performance. This demonstrates massive gains in parameter efficiency. You get better results with a much, much smaller verification model.
So it achieved that 9x efficiency you mentioned earlier. That's seriously impressive. And did it solve that scaling bottleneck problem, the issue where performance flatlined after N8 samples?
Yes, completely. That's one of those striking results. While the baseline PRMs, even the huge 72B one, saturated early, for example, on numerical reasoning tasks, the baseline plateaued around 75% accuracy after N16 Tattoo kept improving. Its accuracy on the same task continued to climb significantly from N8, around 74%, up to N32, over 78%. It effectively utilized the additional samples in compute.
So it doesn't hit that wall. It keeps getting better as you give it more solutions to evaluate, which is what you'd hope for.
Exactly. It scales gracefully. And this wasn't just for the standard best of N sampling method either. They tested it with other advanced inference strategies like beam search and something called diverse verifier tree search, DVTS. The improvements held up. For instance, with beam search, Cat2 boosted accuracy significantly more than the baselines, which again tended to saturate.
So the benefit is robust across different ways of using the verifier.
It seems so. And theoretically, it ties back to that reward decomposition. Their Theorem 4.1 basically provides intuition that by separating the reward into rare reasoning and their table ops, the improvements contribute additively. You're ensuring targeted, effective supervision on both the general thinking and the tricky table-specific steps, which is where the old models were failing.
Okay, that makes a lot of sense. You're fixing the weak link without compromising the strong parts?
Pretty much.
So let's recap this journey. We started seeing how even giant AI models struggle with simple tables, and worse, their verifiers often fail too. We diagnosed these hidden flaws, the PRMs being blind to incorrect data retrieval, and the short-term memory or locality bias causing errors in using table data over time.
Failures in grounding and long-range dependencies.
Then we saw how Tattoo is built specifically to address this, using that clever reward decomposition to focus supervision, and crucially, integrating external tools, calculators, data lookups so the verifier doesn't guess, it checks objectively.
Right. Shifting from subjective internal reasoning to objective external verification for factual steps. And using that dual-stage training, especially the RL part, to really instill that delegation behavior.
And the results speak for themselves. Huge accuracy boosts, beating models 9x its size, and finally breaking through that performance scaling barrier for tabular reasoning.
It really does highlight a broader point, I think. This work strongly suggests that for complex, structured, factual data like tables, our verification models can't just be language experts. They need to evolve. They have to incorporate mechanisms, like these external tools, for objective, fact-based checking. Otherwise, we'll just keep hitting these performance ceilings whenever the data isn't pure text.
That leads perfectly into our final provocative thought for you, the listener. Tattoo was designed for text and tables, integrating computation and lookup tools. It worked incredibly well. So if adding those specific tools dramatically improved verification for structured data, what's next? What happens when we think about multimodal inputs? Imagine verifying reasoning over charts or graphs, or even tables embedded in images.
Yeah, what kind of tools would PRM need then? Maybe specific image analysis tools? chart reading utilities, data extraction modules.
Exactly. What new forms of tool-grounded thinking will the next generation of verifiers need to master to handle the sheer diversity of information they'll be asked to reason over? It seems like just being good at language won't be enough anymore.
Definitely food for thought. The era of purely text-based verification might be ending, especially for complex real-world tasks.
Something to ponder. Thanks for joining us on this deep dive.
Thank you.
We'll see you next time.